Here are the variables we have. We have the mass of the human, the initial height of the human above the Earth's surface, mass of the Earth, gravitational constant, and the radius of the Earth. So we want to find the final velocity of the diver with respect to these variables right here. First thing I can think of, since we're dealing with, looks like an energy transfer problem, is we're going to use the work energy relation. Okay. Now we can use the conservation of energy with gravitational potential energy as well, but we haven't formally derived it yet. So we're going taking a step back to a more fundamental principle and going from there. So W is basically force of gravity dot ds, and delta kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. First thing I'm going to do is just informally start knocking a few things out. The skydiver, I guess if you will, is starting from rest, so the initial velocity is going to be 0. Force of gravity for all situations not near the Earth's surface, we'll assume it's not near the Earth's surface, is going to be g m m over r squared. So let's go ahead and take this and kind of create a more appropriate equation. From, we'll say h plus re, so that's the height of the Earth's radius plus the height above that surface of the Earth, all the way to RE, which is the surface of the Earth. That's where the cliff diver, or not cliff diver, but skydiver is going to fall to. We're going to say G M M E over R squared. That's the force variable and how it varies from the starting condition to the ending condition. And then we're going to have ds, which is the infinitesimal distances that the skydiver falls throughout. Now, I'm not comfortable enough with this yet. I'm going to go ahead and just complete the equation first. I'm not comfortable about this yet because we have this in terms of ds. This is in terms of r. So again, looking at the picture here, you have this diver way up here, and this is an exaggeration, obviously. You have the height plus Earth's radius right here. The diver could be at any point. So let's say the diver's here. That's going to be an R variable. And in terms of the distance that the diver went, that's going to be an S variable. So you can say that R plus S is equal to H plus RE. All right, so that means that ds, or I'm sorry, let's get ahead of myself and say ES is equal to H plus RE minus R. So now if you were to take an infinitesimal s ds, that's going to be infinitesimal change H plus RE minus an infinitesimal change R of dr. Now, H plus RE are constants, so there are no changes happening. So the d of H plus RE is going to be 0. And that leaves ds equaling to negative dr, similar to that last problem we did with the meteor. So now let's go ahead and write that in. We'll do a variable transformation from ds to negative dr. We're going to have H plus RE being the initial height of the diver, RE being the final height, GMME over R squared. And now it's going to be negative dr. I put the negative out in front. It's going to equal to 1/2 mvf squared. And we are looking for the final velocity. So let's go ahead and solve this and then solve for VF. Bringing out the constants G, M, ME, I'm going to have left in the integral 1 over R squared dr. And that's going to still equal to this thing right here. The integral of 1 over R squared is going to be R to the negative first power divided by -1. So going here, we're going to say r to the negative first power over -1 from h plus re to re. And let's go ahead and get the negatives out. And let's put this on the bottom and input the limits of integration. G, M, ME, 1 over RE is replacing R in this case, minus 1 over RE plus H or H plus RE equals to 1/2 MVF squared. And now we just solve algebraically for VF. M's cancel out, and we're left with VF equaling to square root of 2G ME 1 over RE minus 1 over RE plus H. Plugging in all the numbers, actually, we don't have any numbers. Getting in terms of the variables, let's just make sure we do that first of all. We have G, we got ME, we have RE, we have RE again, and we have H, and we didn't need to invoke M. This is the final answer. This is the velocity of a skydiver, let's just say, starting from a height h above the Earth's surface and crashing into the Earth. This is assuming there's no air resistance.